We had seen last time that the core collapse supernova produces a lot of neutrinos, about 10 to the 57, 10 to the 58 neutrinos. Basically, the entire gravitational binding energy of the pre-supernova star is converted into those neutrinos. And I also mentioned last time that there had been a lot of developments recently in modeling those supernova, which I will not talk about, but I think Tony Mezzacapa had talked about that already. Well, one thing that we are hoping to do is to be able to observe these neutrinos in great detail. Well, of course, they have been observed already. I mean, this, as I pointed out last time, this is the observation of neutrinos from supernova 1987A, but not too many events, as you can see. We are hoping that next, who knows how many years, there will be a supernova, and we will be able to observe that supernova in neutrinos. Now, if you want to catch a supernova in neutrinos, you'd better know what neutrinos do inside the supernova. I love this picture. This is from the Symmetry magazine. It's, I missed most of the baseball season. I was in Munich, but San Diego is a great baseball city. Padres play here, and Brooklyn Dodgers are playing up the road for like 40 years. Okay, so the first thing I should do, introduce the neutrino flavor isospin. And again, this was mentioned a number of times, but it's good to give a proper definition. Basically, this is an isospin. It's a degree of spin in the flavor space, neutrino flavor space. Let's say that you take only two neutrinos, two flavors, and let's say it is electron and muon neutrino. And you can define electron neutrino to be weak neutrino isospin up and muon neutrino to be neutrino isospin down. That's not a big deal. Now, there are a lot of neutrinos in a core collapse supernova. It's a many-body situation. So it's good to use the language of many-body physics. So I will use creation annihilation operators. And actually, Vincenzo also used them yesterday in his lecture. So I will indicate an operator that annihilates a muon neutrino A mu and creates an electron neutrino AE dagger. So these are the neutrino creation annihilation operators, and they either annihilate or create fermions. This neutrino flavor isospin can be written formally in terms of these operators in this particular manner. So 1/2 AE dagger AE minus A mu dagger A mu is the third component of the neutrino flavor isospin. This is the angular momentum creation operator, and this is the angular momentum annihilation operator. And those three operators you can easily show that close under SU2 commutation relations. So that's actually well known. And these operators can be written in either mass or the flavor basis. You can do either one. So for example, if you want to go from this flavor basis to the mass basis, you just introduce the neutrino mixing of those operators in this particular way. Remember, typically when we write the neutrino mixing matrix, we write that in terms of spinors, which are given in the position space. These are basically Fourier transforms of those spinors in the momentum space, right? So you can actually write down in Hamiltonian that describes neutrinos using such operators. So for example, if I take out an identity from the Hamiltonian, the A1 dagger A1 is the number of neutrinos with mass eigenstate M1, and A2 dagger A2 is the number of neutrinos with mass eigenstate A2. If I take out an identity, then the energies of those neutrinos are M1 squared over 2e or M2 squared over 2e. So you can write down a free neutrino Hamiltonian in that way. It's kind of straightforward. The same Hamiltonian you can easily write down in the flavor space using this transformation. If you do that, you get this particular expression. Now, of course, this is not surprising. If you, instead of these operators, and I can rewrite these operators in terms of creation annihilation operators, and let me do that. So instead of these operators, I'm going to write them in this form. So this is the free neutrino Hamiltonian, and this is not surprising because if you simply take the 2x2 representation of the angular momentum operators, then you get the simple 2x2 neutrino mixing matrix that you had seen. So this is quite straightforward. In principle, one body problem is very straightforward. You don't have to do anything fancy. So then you can add an interaction with the background electrons, which gives rise to the MSW effect, again to this Hamiltonian. If you do that, it takes this particular form. So then you bring this extra term, but it still is proportional to J0, so you're fine. Okay, this is straightforward, and this problem, of course, can be exactly solved. Has been solved numerous times in numerous papers exploring MSW effect. Okay? However, since there are so many neutrinos, as we had seen yesterday in a core collapse supernova, you cannot actually ignore neutrino-neutrino interactions. And if you actually calculate, you start with the current-current interaction Hamiltonian, written in terms of spinors, take the Fourier transforms, and then look at the coherent scattering limit. If you do all that, then you find that the neutrino-neutrino interaction Hamiltonian can be written in this particular form. Here, again, J sub p is that angular momentum algebra for neutrinos with momentum p, and J sub q is the same angular momentum algebra for neutrinos with momentum q. And because of the current nature and the V minus A nature of the weak interactions, then you have this additional term, which is 1 minus cosine of the angle between those two momenta. Now, of course, the Hamiltonian, I'm writing the Hamiltonian, not the Hamiltonian density, which is more common in field theory. And since we are doing the Hamiltonian, there are these integrals. And since there are really two of these operators, those integrals, if you do everything carefully and use box normalization, bring in a factor of 1 over v. Now, this is all very good. So this term, though, makes the many neutrino gas interacting in a core collapse supernova a genuine many-body problem with 1 and 2 body interactions. And those of you who studied many-body physics know that in general that problem is not solvable. It's very, very difficult. You can only solve exactly. By exactly, I mean either analytically or numerically, only exactly in a number of very limited cases. So this becomes a genuine many-body problem. And here is the Hamiltonian gory detail. This is customary to introduce this vector b, which is a stationary vector written in terms of these mixing angles in this, so that the first term can be written, the free neutrino term can be written as b dot j. Now, again, this volume factor here is important because, as I mentioned, this is the Hamiltonian, total Hamiltonian of the problem. That's what I'm writing. If I write down the Hamiltonian density, like is the case in the field theory, then I need to divide this by another v. So those v's divide these operators, and eventually they give me densities. And then you can write everything in terms of those density matrices. And again, I bring another factor of v here, but since I have two j's here, it's okay to write densities. So this becomes the difficult problem to solve. And as far as I know, it's not that easy to solve. And as far as I know, no one has managed to solve it exactly. It's a very complicated problem. but it's important to solve for the supernova physics. So many times what people do, at least in the past, at the beginning, what people did, they assume that this angle averaged to a finite value, fixed value. They call that single angle approximation. Then this problem simplifies quite a bit, and in that limit, there are actual interesting solutions. Now, I have only written down this Hamiltonian for neutrinos, no anti-neutrinos yet. It's very easy to introduce anti-neutrinos. You then introduce a second set of SU2 algebras. Also, everything I have done is for two flavors. It's very easy to introduce a third flavor. Then it requires introduction of not one, but two SU3 algebras, one for neutrinos and one for anti-neutrinos. I'm not going to go into detail. Both expansions are, both extensions are straightforward, but quite tedious, and you can read the details there. Now, but I should point out that this is the only many-body system I know that is driven by the weak interactions. And just if you compare this with the other many-body systems we know, like nuclei, where nucleons interact primarily, I mean, the nuclear physics is driven by the strong interactions, but you have at most about 200 particles, lead 208. Similarly, in condensed matter system, the driving interaction is electromagnetic, and you have at most an Avogadro number of systems, but typically it's much less. The particles or the objects that participate in the many-body physics are much fewer in a typical condensed matter systems. But in the case of neutrinos in a supernova, you are dealing with a system, a many-body system, which interacts with weak interactions and has as much as 10 to the 57, 10 to the 58 particles. And this is actually a perfect example that astrophysical extremes allow us to test physics that you cannot test in any other way. As a matter of fact, the neutrino-neutrino interaction is in the standard model. It's not new physics, but there is no other way to test that interaction except in this particular problem. Now, I mentioned that this problem is hard to solve, and many times people do a mean field approximation to solve that problem. And I will sketch that approximation again. Since most of you are not formal theorists, it may not be necessary for you to do this, but nevertheless, I think it's good to sketch it a little bit. So basically, what we really need to do, we have an Hamiltonian which has one and two body interactions, h nu, the standard ms double the term, plus this neutrino-neutrino interaction term. And we need to solve the evolution equation for the system, this particular equation. That looks very straightforward. Well, what I would like to do, write this evolution operator as a path integral, Feynman path integral. And of course, if you write a Feynman path integral, you have to define a basis. You have to define a basis, a complete basis to define the integral. And as a complete basis, I will use the basis of SU2 coherent states, which is given by this. And here, this is the analog of the Slater determinant. It is the state which is occupied by only electron neutrinos. So if you do that, you get a nice expression, at least formally, a nice simple expression for this evolution operator. Of course, Feynman was an extremely intelligent man, but writing something down as a path integral doesn't mean that you can calculate that path integral easily. However, you can calculate that path integral approximately. As a matter of fact, here there is the action associated with the path integral, which then, of course, depends on the parameters of the coherent states. So the path integral basically is an integral over paths where each path is weighed by exponential is, where s is the action. Of course, all paths contribute in general. This is basic quantum mechanics. As you go from here to there, you know, if any path, direct path goes on, another path, maybe there's another path that goes all the way to Perseus cluster and back, that contributes too, but its contribution has to be small. So the maximal contribution is when this quantity is stationary, that probably we had seen as the least action principle in our classes. And if you look for the points where it's stationary, you end up with some equations. These are called Lagrange equations in classical mechanics. If you solve those equations, you basically get this expression. So this is a mean field type expression. And this is a, of course, still very complicated problem. It's a very nonlinear Schrödinger evolution problem. But it actually then deals with a mean field defined in this particular way in terms of those integrals. So basically, what you do, you take this many body problem with many neutrinos interacting, you reduce it to a problem where you have a test neutrino which interacts with the mean field generated by all the other neutrinos. And of course, it is this problem that is solved by many people. And even then, many people still solve this problem, at least in the past, in the single angular approximation. Now, I don't really want to, this is again perhaps a bit too formal, but I want to point out one thing here, and that is this Hamiltonian is actually analogous to the Hamiltonian of the BCS theory of superconductivity when the angle is averaged over. So these two Hamiltonians then have the same symmetries leading to the same dynamics, dual dynamics, if in some sense, because the problems are different physically. Mathematically, they are similar. In the case of BCS Hamiltonian, you are dealing with pairing of fermions. Pairing is an attractive force, so there's a minus sign here. Here I wrote everything only for neutrinos with the plus sign. Of course, anti-neutrino-neutrino interactions have opposite sign. So it's a much more complicated. This is a stationary problem. This is a continuum problem. But nevertheless, there is a formal analogy between those two. And if you use that formal analogy, you actually derive these conserved quantities. These quantities are conserved. It doesn't matter what happens during the evolution. This quantity will always remain constant. You can show that very rigorously, if you wish. Now, this is all very good, but I know people don't like equations as much. Well, some people do, but most people don't. And you like graphs. So let me show you a calculation of this conserved quantity. So what I'm going to do, I'm going to assume that the supernova fluxes are like this as they leave the neutrinosphere. So this is the nu E, this is the nu E bar, and this is nu mu, nu tau, nu mu bar, nu tau bar, and so on. So these are the initial fluxes. You can start with any initial flux you want. It doesn't matter. And these are the conserved quantities for these initial fluxes. So this is the conserved quantity for neutrinos, and this is the conserved quantity for antineutrinos. These quantities are conserved. As soon as you take these initial distributions, this is what you get at all times for these conserved quantities, even when they reach to your detector on Earth. So it's of course nice to have a conserved quantity, but the second thing is that this is a great thing so that you can test your numerical evolution code. At each point, that quantity has to look just like that. Yeah?
Is this done in the single angle approximation?
Yeah, this is in the single angle approximation.
The single angle approximation preserves this conservation law?
Yeah. The conservation law I'm now showing here is in the single angle approximation. Multi-angle is much more complicated, and I'm not going to go into that. It's much more technical. Okay. Now, another thing is...
There are regimes, though, where single angle calculations can capture
sure.
the essential features.
Of course.
Other regimes don't.
Right. I mean, I'm not saying this is always physical, but just to illustrate the effect here. This is in the single angular approximation, where it may describe physics in certain cases. But this is a conserved quantity, and it remains that way all the time.
Can you write down conservation law in the multi-angle approximation, in the multi-angle case, full?
Well, the answer is almost. it's almost conserved. There is a quantity which is almost conserved in the multi-angle approximation. We are writing a paper on it right now. I don't have the final result. Almost. There is a little bit, a little perturbation, if you wish, that doesn't get conserved. But that's actually a very interesting question, of course. Now, there's one other thing. In the case of BCS Hamiltonian, typically we solve it going to what we call a quasi-particle basis. Basically, you diagonalize this Hamiltonian in a rotated basis, just like the way we diagonalize the mass Hamiltonian, the free particle, free fermion Hamiltonian earlier in the first lecture. You can diagonalize this Hamiltonian in a rotated basis. But when you go to that basis, quasi-particle basis, that doesn't conserve particle number. In order to conserve particle number, when you do quasi-particle approximation to the BCS Hamiltonian, you introduce a Lagrange multiplier to enforce the particle number conservation. And that Lagrange multiplier turns out to be the chemical potential of the superconducting system. Now, you can do the same here. Again, in the single angle case, you can do the same here. You can start with this Hamiltonian and go to this quasi-particle basis to diagonalize it. Diagonalize it in that basis. Of course, that basis doesn't conserve the neutrino number. If you enforce the neutrino number conservation with a Lagrange multiplier and finish the diagonalization, that Lagrange multiplier turns out to be the split energy that is numerically observed in those calculations. Now, I don't have an analytic proof of that statement, but that always had been the case in all the examples that we studied. Again, I'm working on an analytic proof of that. So this is, if that is the case, if I can come up with a simple statement like that, then at least in the single angle case, and possibly in the multi-angle case in an approximate way, you can get the split energies without actually doing split energies themselves, not the full spectra. Split energies themselves without actually doing the numerical calculation, which actually would be very nice. But anyway, if nothing else, these conserved quantities help us to actually calculate, check our calculations as we go on. Okay? Well, I'm sorry, this is a little bit too technical, but any questions about this? No?
This would be completely. So in BCS, one way to understand BCS, right, is that the spontaneous symmetry breaking and so on. Is there an analog?
Well, I mean,
I'm sure you thought about it.
yes, yes. I mean, actually, Nambu, who basically invented the spontaneous symmetry breaking idea, he came up, I mean, if you were not here during my first lecture, right? But if you write down the Dirac matrix, right? Well, let me give a more physical argument than that. So let's say that you have fermions, right? Fermions are such that their energies are p squared plus m squared square root, right? Square root of p squared plus m squared. And you can think about negative energies for antiparticles. I mean, that's one way to formulate that. So the antiparticles would have energies minus square root of e squared plus, k squared plus m squared. So the lowest energy that you can have for a particle is plus m. The highest energy you can have for an antiparticle that way is minus m. So there's a gap in the energy spectrum of 2m. So that gap, Nambu argued, is analog to the analog to the pairing gap in superconductivity, which actually is, if you write down the equations, mathematically they're equivalent. He argued that that is the analog of the pairing gap. And then he introduced the so-called Nambu-Yonah-Lasinio model, where he added a quadratic interaction, which is exactly the same interaction that Higgs interacts with. This is phi square type interaction, square root. And then he went again to quasi-particle basis and showed that indeed there is a spontaneous symmetry breaking. There are two phases. One is the superconducting phase. One is the perturbative phase. And the transition is discontinuous because it goes like 1 over m, if you wish. So indeed, yes, you can try to connect these ideas. And that's how Nambu came up with the idea of spontaneous symmetry breaking. Basically, he treated mass as a pairing problem. I mean, he treated mass of the fermions as a pairing problem, and indeed it is. Mass is the pairing between left and right-handed components. Now, okay, then came Pauli, much after he introduced the neutrino in 1956. He introduced a Pauli transformation which actually mixes a field with its charge conjugate. So it's a transformation where psi goes to cosine psi plus sine, cosine alpha psi plus sine alpha psi to the charge conjugate, right? This is called Pauli transformation. And then Gürsey came and he generalized that, but so it's now called Pauli-Gürsey transformation. Now, if you apply that transformation to Nambu's theory, you don't get only the Dirac masses, but also the Majorana masses, which is the amazing part, because Majorana knew nothing about that. And you can apply the same ideas to that. So you get a complete, it turns out the most general symmetry associated with pairing is SO5. So everything sits in an SO5, but you can put the Dirac mass, Majorana mass, both left and right-handed, this transformation, and the seesaw transformation, all of them in that SO5, treating it as if like a pairing problem. And you can apply spontaneous symmetry. But I don't think those ideas had been explored any further. But indeed, there is an analogy. Maybe this was a longer answer than you wanted, but sorry about that.
Thank you.
Okay.
Can I ask about Christina's neutrino anti-neutrino correlations?
Right.
In her quantum kinetic BBGKY hierarchy treatment of the decay. So, do you have any insight as to how that's related to this? Yeah. I would think there would be a.
Yes, in some sense. Okay, can I go to another talk for? Okay, in principle, yes. Yeah, this is another way. Let me go to just very quickly. Okay, I'll go down in this. I'll show you one transparency from another talk, if I can. Yeah. So this is another way of introducing the mean field approximation, right? Basically, okay, the idea is this. You want to solve an Hamiltonian with two-body interactions. But two-body interactions, I mean, this is actually general enough, not only this transparency, but I'll come to that in a second. Two-body interactions are very hard to deal with. We don't want to deal with them. What mean field theory does, it replaces those two-body interactions with appropriately chosen one-body interactions. One-body interactions are easy to do. That's ordinary quantum mechanics, single particle moving in a potential. So basically, instead of having a two particle interacting, you try to write that as one particle interacting with a potential, which looks trivial, but it actually isn't. So one way to do that, you typically have two quantum mechanical operators, and the product of them is the two-body interaction. So what you do, you try to find a state so that you can rewrite this in this particular form. You can basically replace one of the operators with the expectation value of that operator in that state. And then, of course, you have to do the same for the other operator. But if you do that, there is a bit overcounting. So you have to subtract that term. So that is the standard mean field approximation. That's what we do in the mean field approximation. But the thing is, if you look at this product, if you take its expectation value of the whole product, again, this has to be satisfied. So you need a state for those operators. Given two operators, you need a state that satisfies that condition. But this is the mean field approximation, if you wish. So what we did, for example, is to to treat both neutrinos and antineutrinos. And we did not have the interaction terms, we did not have the operators that convert neutrino into antineutrino. In other words, if you create an annihilation operator for antineutrinos are C and D, and for neutrinos are A and B, we did not have A dagger C type operators. We did that as A dagger B and C dagger D. So neutrino, antineutrino. But you can do the other way. So basically what she did, she found states in the other way. She mixed the other two. So that's what she did, if you wish.
Sorry to
Yeah.
I tried to understand the paper. I read it. Those are really correlation between states, neutrino-neutrino states with opposite momentum.
Yes.
So it's really reminiscent of pairing.
Yes.
And this has nothing to do with what, let's say, Alexei talked about yesterday.
Yeah.
Neutrino of same momentum is a different kind of correlation.
Is it? I mean, well, first of all, they all look like pairing. Even the ones Alexei talked about is like pairing in some sense because, I mean, they all look like pairing, right? It's not like some look like pairing, some don't. It just look like different nodes. They all look like pairing. But indeed, she looked at the neutrino, anti-neutrino correlations of, yeah. Well, so they have to be suppressed, presumably, the modes that she looked at. But again, remember, this is all then mean field theory. You do not know if everything is physical a priori. You have to do the calculation and figure out if it's physical. I mean, in mean field theories, until you actually look at everything, then you do not know if the approximation you did is physical. As a matter of fact, a lot of times it's not physical. You have to have fudge parameters. I'll come to that. Okay, so all right, so the topics of my lecture was frontiers in neutrino physics, this lecture officially at least. So I have to tell you a few other things about neutrinos besides what we have discussed so far. And I figured since we are in San Diego, I should talk about Maria Mayer a little bit. She was awarded the 1963 Nobel Prize for shell model, her work on shell model, actually precisely figuring out that you need spin-orbit coupling in the shell model. And eventually, this work was in 50s and 40s. And in 1963, she got the Nobel Prize, and San Diego Union had a headline saying that San Diego housewife wins Nobel Prize. Now, she did other things too, not just the shell model. And one of the things she did is that she figured if the neutrinos can beta decay, I mean, if neutrinos are produced in beta decay of nuclei, that's a typically perturbative process. The second order perturbative process should also be possible. And that's what we call double beta decay. She's the one who first explicitly proposed that there should be double beta decay. So I want to tell you a few things about double beta decay and how it connects to neutrino physics as we study. So this is the double beta decay, right? I mean, so a typical beta decay, nucleus emits an electron and an antineutrino or positron and a neutrino and goes on to a daughter nucleus. So that's the typical beta decay. But if this process can happen twice, typically it's calculated in perturbation theory, you can do it twice. And then this is what we call two neutrino double beta decay. This is the standard second order process. This is the process that she said has to exist. And this process has been observed for quite a few nuclei now. It's a very rare process. It's very, very rare. But nevertheless, people managed to observe it. And actually, I think she was at Argonne when she proposed that as well, not in San Diego. But I don't know. So the thing is, though, the neutrino is going out, right? She was at university. Well, did she actually have a position at Chicago? Her position was Argonne.
Our understanding is she didn't have a real job because her husband had a job at the university.
Yeah, they had nepotism rules at the time. No two family members could be employed by the same employee. But anyway, so if the neutrinos are Majorana type, then they are their own antiparticles, if you wish. When you do charge conjugate the standard neutrino, it becomes antineutrino. Then you can actually, this neutrino emitted in the first vertex can be absorbed in the second vertex, such as that. Then you would also have a double beta decay. Namely, a mother nucleus will come, give rise to a daughter nucleus, and two electrons would be emitted. But you would not see the two neutrinos. This is the neutrinoless double beta decay. And that is actually very important to observe because it tests the Majorana nature of the neutrino physics. And it also is a fundamental process because it tests if the lepton number conservation is a good symmetry of nature or not. So it's a fundamental thing. Now, of course, this happens all the time, perhaps you would think, but it doesn't. It happens, again, because of a physical property, the same physical property we had been discussing the last 15 minutes, pairing. The fermions like to pair up. And the pairing lowers their energy. So that means if you have a nucleus with an even number of neutrons and even number of protons, neutrons and protons pair up. So the energy of that nucleus, the ground state energy, is low. Whereas if you have an odd even nucleus, namely if you had an odd number of either neutrons or protons, anything that can pair up will pair up, but you will have an odd neutron or odd proton left over. And that actually raises the energy. And because of that, you get something like this in terms of the binding energies. If you say you fix the A and plot the binding energy as a function of Z, odd even nuclei would be more energetic and their ground state energy will be much higher than the energy of the even nuclei. And this is fundamentally a property of the pairing process. That means, if you look at this carefully, this nucleus here cannot decay into the next nucleus via double beta decay. It's energetically not possible. And because of that, it can only decay in one nucleus over, but that beta decay is a double beta decay. So you can only have, you can always try to have double beta decay, of course, but it's going to be suppressed significantly. You can only observe a even two neutrino double beta decay if that is satisfied. And there are not too many such nuclei where that is satisfied. So for example, germanium-76 is one such nucleus. The next nucleus to it is higher in binding energy. So you can see that you cannot have this beta decay, but you can have this double beta decay. So then it is this process that you have. So this is what Maria Mayer had first guessed, that this process should take place. Of course, physically they're very different because the 2-neutrino double beta decay can only proceed in the intermediate state via 1+ states because of the nature of the weak interactions. Whereas the double beta decay can proceed, since you're summing over all possible states, via all sorts of states. And what matters, of course, is the properties of neutrinos, but also matrix elements coming from the nuclear physics. The matrix elements are quite different in two cases. In the 2-neutrino double beta decay, matrix element is basically second-order perturbation theory matrix element given by this expression that you had seen in quantum mechanics classes. In the neutrinoless case, this is the matrix element. Well, this actually is, of course, the sigma here is the non-relativistic reduction of the weak interactions. So this is actually similar to Alexey's spin flip term, if you wish, in that sense. And these are the isospin operators, since you convert protons into neutrons, ordinary isospin operators. Now, the thing is, this process is happening because neutrino is being exchanged. So this is like the Coulomb scattering where photon is being exchanged. So you have a potential very similar to the Coulomb potential, which goes basically like 1/r. Basically, not completely, but basically. If you calculate that potential, it actually looks like 1/r. So it's actually a rather different process. Well, one thing though, in such a process, the nuclei can pair up. And not only they can pair up with the total angular momentum 0, but they can pair up in such a way that the total spin or angular momentum of that pair is non-zero, or 2 or 4 and so on. And they actually tend to cancel each other. And you can actually calculate all those. And you have a whole bunch of numerical calculations at the moment, but there is no observation yet. One final thing I should point out, that double beta decay, I mean, this is an especially interesting property of nuclear physics. Nuclei change a lot as you go from one nucleus to the next. The nucleus right here may be spherical. As you go one nucleus over, you can start getting significant deformations, and 2 nucleus over can be very deformed. Double beta decay is basically overlap between 2 wave functions of 2 nuclei, one apart. I mean, they're not next to each other. So those 2 nuclei can be very different. One can be spherical, one can be quite deformed. As a result, that actually makes that overlap to be very small, because different wave functions, when you take their overlap, will be giving you a small number. And it's actually, here is a calculation to show you that. This is the deformation of the mother nucleus and the daughter nucleus. This is the mother nucleus, this is the daughter nucleus, this is the deformation. And this is, you can see that the deformations have to match one another to get a significant double beta decay. Double beta decay has not been observed. I mean, it has been proposed by a San Diego professor, but has never been observed. But if we observe it, neutrino's double beta decay, if we can observe it, then it's a fundamental thing. It'll tell us that the lepton number is not conserved. Total lepton number is not conserved. We know electron lepton, muon lepton, tau lepton number is not conserved because we have neutrino oscillations. But at the moment, the total lepton number is being conserved. If we can observe this, then it tells us that total lepton number is not conserved. Okay, I think I'm going to stop here. And so thank you very much for coming so early in the morning for these lectures. And I'll stop and ask if you have any questions. Maria Meyer.
Oh, okay. I thought you were going to be Brooklyn or something.
Oh, no. Yeah.
Okay, so you said if we observe the neutrinoless double beta decay, we basically know that the neutrinos are Majorana particle.
Right.
Now, is there some point where we might get a limit and say, okay, we've looked so hard and we didn't see it, so it cannot, like, can we get to a point like that, or?
Unfortunately not, because we don't really know the nuclear matrix element to that accuracy either. Well, but you realize there is one other way to think about whether neutrinos are Majorana or not. Can you guess what it is? There's one other way, if you can guess if the neutrinos are Majorana or not. Not that easy. I don't think it's practical, or it's not going to be possible for a long time. Well, okay, let me ask the question a different way. What are we talking about? We're talking about mass. But Dirac neutrinos and Majorana neutrinos have different kind of masses. When does mass become important? Is what? In the non-relativistic limit. Can you think about non-relativistic neutrinos? Exactly, cosmic background neutrinos. Their Majorana nature may be important, and you may have features that distinguish Dirac and Majorana neutrinos. So that's another possibility. As I said, I do not know any practical way of doing it.
I guess I don't understand. How does the CMB, the cosmic neutrino background?
No. Cosmic neutrinos are non-relativistic. So as a result, you may be able to think of something where their masses play a role. So for example, as I said, this is not practical. Imagine they're scattering from electrons. You can't measure that easily. I'm not saying you can measure, but imagine that you have a non-relativistic neutrino that scatters from electrons. Its angular distribution for Majorana and Dirac will be different. You can calculate that.
So this would be SZ for cosmic neutrino background.
Yeah,
Yeah.
that's exactly right.
Exactly.
That's exactly right.
Exactly. So cosmic neutrinos are another kind where...
So once we detect the neutrino background in the lab, then the next frontier will be doing the SZ effect.
Exactly. I didn't say it's practical. I said there's one other kind of neutrino where that effect is important, could be important.
But not all C nu B. So there's a spectrum of C nu B, right? Some of them
Right.
are very high energy.
That is true. So you somehow need to be able to have an energy. Yeah. Right. I'm not saying this is practical. I'm not saying anyone here will do that experiment soon. But in principle, cosmic neutrinos are non-relativistic. And in principle, they can exhibit characteristics that distinguish Dirac from Majorana.
I enjoy watching theorists luxuriate.
But this is a fact. I'm not saying it's easy. But they are non-relativistic. No question about that, right?
Well, we don't know what the lightest one is.
Right, that's true. We do not
So
know
that
what
one might not be. But
That's true. That's true. We do not, the lightest one may be even massless. It will be weird, but
it could be a millivole.
right. I mean, look, to make something massless, you need a symmetry that keeps it massless at all energy scales, and we do not know any such symmetry. So, but anyway. Question? Yeah.
So in the neutrino quasi-particle description, the quasi-particles are basically the flavor isospin modes.
In the isospin. Well, but they mix isospin modes, of course, right?
Yeah.
I mean, they can be either mass mode or isospin mode, right?